Okay guys, this voiceover is a little bit after the fact. I just want to point out this beautiful picture. It's actually, they are modeling a wave model, okay, for the actual positioning of your electrons. Okay? Those are the orbitals that we are talking about in your chemistry. So really interesting stuff to learn, but that kind of higher level will be later for you in university. We're going to start from the very beginning. So future me, let's go. Hello. Good morning, good evening, good night. We are in the video here to talk about nuclear physics. Okay, so this is just a pretty short, sweet little dessert for your AS syllabus because it's going to be the last topic. All right, and in this chapter, right, it's a very easy chapter. Past year questions are easy to do provided you know the facts about the reactions that we're going to discuss today. So we're going to roll off the beginning of it by talking about what is a nucleus and what is an atom and what is the key cornerstone experiment that helps us understand what an atom is made out of. Okay, I know you know the answer, but let's go. So this is known as the alpha scattering experiment. So I'm just going to show you the setup here. On this side, right, you have a source of alpha particles. Now pause a bit and think about what are the properties of your alpha particle. So for example, I know that the alpha particle is positively charged. So it has a positively charged, and it's also fairly, I mean, it's not very heavy, but it is, the symbol is 4,2 helium. So that in terms of atomic mass unit, I know I'm skipping ahead, but I think all of us got take chemistry lah, huh? So in terms of atomic mass unit, the helium is heavy, but nowhere in comparison to what is ahead of it, because what we're going to do is we're going to accelerate and shoot the alpha particle. Insert shooting sound effect here, pew pew. Okay, we're going to shoot it towards a thin gold foil. So we're going to assume that the gold foil is malleable, so we roll it until it's so thin, such that there's only a few layers of atoms. So going to be like this. Okay, this one atom of a gold foil. And then we're going to surround the whole thing, like surround sound, by a circular fluorescent screen, because where the alpha particle hits the fluorescent screen will turn green, bright green. They'll be glowing. So they noticed that most of the alpha particle will pass through undeflected. That's the first observation. Okay, so if you look at some drawings that I've given you here, most of it will pass through undeflected. Okay, there's an old past year that asked you to draw this lah, but yeah, you do lah. If you're the type that do past year from 2002, you will encounter it. If not, then no need lah. So this is the first observation. Most alpha will pass through undeflected, meaning this one is the alpha, pass through undeflected, all this. Okay, and because most of it can pass through undeflected, our conclusion would be atoms consist mostly of empty space. Much empty. In fact, just to give you a rough estimation, right? If let's say I were to blow up the model of a nucleus, let me adjust a bit. Okay, if I were to blow up the model of a nucleus such that the nucleus is 1 meter, do you know where is the first electron? It's 10 km away. That is how much free space you have. Imagine a Chinese dining table, the circle one. If that is the size of your nucleus, your first electron, your 1s2, 10 km away. Okay? So that's why we say the atom consists of mostly empty space. Because that's why so much empty space, right? The alpha particle will just pass through in a straight line. So it will pass through undeflected, okay, as seen as this part. Okay, but some of the alpha particles are scattered. And you notice that there are two types of scattering. Some of it will scatter in a small angle. Some of it will scatter in a big angle, in an obtuse angle. Okay, so this is an example of small angle. You go already, you deflect a bit like this. Okay, I'm going to label this one as 2. So this one would be 2. This one, small angle, this is 2. Okay? And large angle, I'm going to make that 3. Okay, so large angle will be this one, 3. So what's the difference between the small angle and the large angle? Well, you can think about it this way. Although it's mostly free space, there's still a nucleus inside. Okay, let me, oh, I got tennis balls, like all respecting physics teachers. Okay, so let's say this is my, nucleus. Okay, if the alpha particle represented by my fluorescent orange pen were to travel through, okay lah, wait, I need 2 balls because we all need to have balls. Okay, so you got these 2 nucleus, okay, and they are far apart. All right, I don't have 3 hands, I'm going to put this down. Okay, so another one is here, far apart, and if the alpha particle passes through the empty space, no deflection because it's a lot of free space. Okay, but if the alpha particle get very, very close, like for example, it get very, very close, alpha is positive, nucleus is positive. You get very close, it will begin to get deflected. So instead of traveling straight like this, it will be deflected this way. So this is a small angle. It's like a glance at the side. Okay, so it's like it might not even touch, just close enough, it will repel and get deflected. Okay, that will be the second one. So this actually tells you that our nucleus is positively charged. So center of the atom is positively charged. I think I type nice faster. Center of the atom is small, small and positively charged. If it's big, then you will have more deflection or more number of alpha being deflected this way. So small and positively charged. Okay. What about the large angles? Well, this is my term again. If I go very close, it will deflect this way. How can I deflect back in this direction? You smack it in the middle. So side view, if you hit it dead center this way, or hit it close to dead center, it will rebound and go back. Okay, hit it close center, rebound and go back. So that would be only possible if the nucleus is very dense. Because if let's say it's a very soft, squishy nucleus, then maybe they collide and then they travel together with a common velocity, and then you have to do conservation of momentum. Okay, so if you look at the example that I will discuss in another video, it is like you shoot a bullet towards something that is like very big, like a bowling ball. The bowling ball is not gonna move much lah, but the bullet will ricochet and rebound, hopefully not shooting someone in the head. Okay, so that is my tennis ball. Normally I use it for kinematics lah, but yeah, put this aside. Alright, so this one shows that the center of the atom is also positively charged. Small, positively charged. Because if it's negatively charged, right, it will just happily absorb your alpha particle because I'm negative, and look at this delicious positive alpha particle come. Okay, so the reason why there's any form of deflection is because nucleus is positive, alpha is positive, positively charged and very dense. Okay, so that's all lah. Normally they ask objective lah. Sometimes they will ask you to write the observation. Sometimes they will ask you what is the conclusion or the inference that you can make from the observation. Help yourself. Okay, so from here we can conclude the structure of an atom, but actually what can be concluded is just a tiny bit of the situation, because we have a nucleus that is positively charged, but we have not yet discovered that the nucleus consists of neutron and proton. The discovery of neutron and proton, ask your chemistry teacher, Google yourself. Now in syllabus, I'm not a video with 2 hours already and then you complain. Okay, so but it tells us that this one is very small and dense, not drawn to scale, this atom. Okay, How did we discover the proton? How did we discover the neutron? How did we discover the electron? We now tell you, though. We just tell you that it consists of proton, neutron, electron. You take it for granted. It's not that easy to discover. Go find out what's the experiment. Okay? Okay, it's actually building on previous people's experiments. Alright, so anyway, so this is a structure of an atom. It consists of a proton and electrons and neutrons clustered at the center. Okay, so if I want to write the atomic symbol for this, right? This one, 6 proton is nitrogen. Nitrogen, 6 protons. I think so, but since I'm not doing chemistry, I don't have to think about it or talk about it. So normally it's represented, let's say this is the atomic symbol. Adjust my pen. So let's say this is X, this is A, this is Z. Okay, so this one will be written as X. This is 12, 6 plus 6, and this one will be 6. So what is on top here is the proton, the nucleon number. I'm also pretty sure you know this already. And what is down here is known as the proton number. Okay, so some basic properties about nucleon and proton number. I'll type this one as I talk. So nucleon, right, is the total number of protons and neutrons in a nucleus. Okay, and proton number, this would be the total number of protons in a nucleus. By the way, I'm also pretty sure you know what is an isotope, right? You can say 2 nuclei are isotopes if they have the same proton number and different nucleon number. Nucleon number sometimes is also known as mass number. Sometimes. Okay, I shall follow the more modern convention. Alright, so when it comes to mass, proton, neutron, and electron, they obviously have different mass. You can find its value in the front page of your exam paper when we normally put the data, or your separate attachment if you're doing this on exam.net lah. Okay, so proton, normally in chemistry we say, oh, it has a mass of 1. This one is not that nice lah. Oops, it's not that nice to think about it as the mass of 1, because there's actually a slight difference in the mass of proton and neutron. So the mass of proton, right, is actually represented by, we can call this 1U, not the shopping complex, okay, 1U, okay, but 1U, right, is 1.66 times 10 to the power of negative 27 kg. Now, I will only use 1U if the question is talking about, oh, you have a nucleus, and the nucleus got 6 proton and 6 neutron, then 12U lor, because the neutron can also be 12U. But if the question specifically asks for the mass of a proton, so maybe you are doing some electric field question, or you are doing some question that needs you to find that involves some form of proton, just pure proton, not proton in a nucleus, then you will use the value in your data booklet, which is 1.67 times 10 to the power of negative 27. Okay, so I'm gonna just crop that in for you. Ding, ding, ding. Okay, so it will be here. I kind of like got it from your table of contents. I mean your table of constants lah. Okay, so this would be the rest mass of proton. But if you use this, you just make sure that you know lah. You can also find this in your calculator, by the way. Okay. And for neutron is not exactly 1.67. Okay, so I'm going to stick neutron to this one because your exam didn't give you a value. Now for electron, right, the rest mass is 9.11 times 10 to the power of negative 31. So this one is this. But by the way, right, you should make sure or try to make sure that your answers are in the appropriate unit, okay? But this is more important if, let's say, you are talking about A2 lah. We will be in this topic again in A2. So in terms of U, we used to tell you, or at least chemistry used to tell you that never mind lah, electron so light, we can ignore. But actually the mass of the electron, right, is 1/1840 U. Okay, value of U is also given in front. Alright, so this charge is positive 1e, but we much prefer in physics to also know the value of E, the electronic charge. Okay, this is obviously determined experimentally. So this one is negative 1e, so negative 1.6 times 10 to the power of negative 19 Coulomb. As far as we know, charge is quantized until the next subtopic, but this one is quantized. Quantized here means your value of charge must be in multiples of 1.6. It cannot be like 1.7 or 0.8, not possible, okay? So quantized here means it has to be multiples of 1.6. Alright, so we're gonna move on. Liao, okay, I think this one is okay. So the next part of the video, besides looking at the alpha scattering experiment and seeing how it contributes towards the structure of an atom, we're going to go through the type of nuclear reaction. Okay, so you have again already learned this, at least the alpha, beta minus, and gamma decay. Okay, so we're going to just roughly compare them because this is just a review, so I plug this from your textbook. Okay, so the alpha particle consists of a fast-moving helium nucleus. So it has 2 protons and 2 neutrons. Very heavy compared to its other radioactive siblings lah. Okay, and the charge is positive 2. Okay, beta minus is a very fast-moving electron. So this is light, it's very speedy. Okay, and a beta minus is a very fast-moving positron. Wait a second, what's a positron? A positron is a, surprise, surprise, positively charged electron. If there is such a thing, yes, there is. Okay, positively charged. So everything is like the electron has the charge of it. It has a mass of an electron, but it is positively charged. What? Why? Okay, you hold on to that thought first. We'll talk more about this later. So it's a very fast-moving positron, okay? And gamma is a short wavelength EM radiation, okay? Electromagnetic radiation. Fondly sometimes known as the photon, light particle ma. Whenever we talk about on, like neutron, proton, electron, all the ons is particle. So we like to call this photon as well, because this is light photo. Okay, so we're going to compare a few stuff, namely the charges. Because this one consists of 2 protons, so charge is positive 2e. Beta minus, negative 1e lo. Beta plus, positive 1e lo. Electromagnetic radiation, 0 lo. Okay, so all this property will make sense if you understand what alpha is and what beta is, and so on and so forth. So for example, alpha is very heavy. If it's very heavy, right, means it cannot penetrate well. You cannot travel far because you're very heavy, you know? Okay? But the ionizing power is high. Ionizing power, right, is the ability for the helium to remove electrons from other molecules. Now, if the helium is very heavy, it is easier for it to knock off the electrons from another molecule. So the ionizing power is high. So if you compare this to, let's say, beta, right? This one is stopped by several mm of aluminium. So it doesn't penetrate. It penetrates better than air. Better than alpha, because alpha can be stopped by air. Few cm of air. So alpha will travel from my mouth to here. Stop there. Cannot even reach your camera. Not very useful unless you swallow it. Then it's a totally different deal. Okay? Ionizing power is okay lah. Because it's easier for a heavy helium to knock off another electron, not that easy for a light electron to knock off another electron. Think about American football. Okay? So if you compare this with the beta plus, now beta plus is a special animal because beta plus, right, is what we call an antimatter. What? Matter got antimatter. Yin and yang. No, nothing to do with yin and yang, but matter, there's antimatter. Okay? So when positron collides with electron, the pair would be annihilated. Because in the beginning, there's the universe, right? And the universe is nothing. Remember the video? So the universe is nothing. And then suddenly, boom, got something. But how can nothing become something? Not possible, right? So what they did was, or the theory that's going right now, which by the way, we can create antiparticles for a very short period of time. The theory that we are running with is, number one, we have matter. And then we have the antimatter. We put together, they disappear, and they annihilate. But what made matter win in the fight of matter versus antimatter? Nobody knows, okay? And because we are matter, we call ourselves matter, and the one that doesn't exist anymore as antimatter. But if we were to meet antimatter, we would just annihilate each other, we kill each other off. So because of this, it's not going to travel very far. There are so many electrons around you. You move your hand like that, you touch a few billion electrons. So no dice, cannot travel, okay? Whereas for gamma, light very high. If you want to stop this, you need lead, not aluminium. Okay? So, ionizing power, very weak. This one cannot even travel at all, does not travel. And this one will also be low because it doesn't have mass, so it's not that easy to steal the electron. If you want to ionize using gamma, what the gamma ray will do is it makes the electron so excited that it jumps away from the orbital. So it's not by knocking out the electron, it's like the electron jumps up a higher energy level and a higher energy level, and eventually it ionizes. Okay, so the reasons for decay are different. For example, a nucleus will react and create an alpha particle out of itself if the nucleus is too big. Okay, so if the nucleus is too big, right, it just means that, oh hey, the helium can lose some proton, some neutron. Okay, beta minus will happen if the nucleus has too many neutrons, because in beta minus, a neutron becomes a proton, an electron. You can think about it this way lah. Neutron is neutral, proton is +1, electron is -1. So +1 -1 is still neutral. Okay, so that means you got too many neutrons. You make your own protons to balance out the number of neutrons. Okay, and the electrons escape from the nucleus. Electron very light. Whereas if you want beta plus, right, it's the opposite. Now you have too many protons. So proton is +1. So in order to balance +1, you have proton. It must become a neutron, which is neutral. And then you have a beta, but this beta must also be +1. So hence it's a positron. And the positron will just be released. Okay? And usually, if you look at the gamma particle or the photon, gamma radiation, Normally, we emit it together with either an alpha particle or another particle, because this one is high energy, it will drop back to a lower energy state. Okay, but of course it can spontaneously happen as well lah. The thing is we won't be able to see it happening on its own. Okay, so here is a few equations that I will write for you now regarding the decay, and talk about more properties about alpha and beta respectively. Alright, here we are, and we will start writing down the equation for the different types of decay so you can differentiate them and answer questions. Alright, so we're going to start off with the alpha decay, okay? And normally you are not expected to know how to memorize the equation, but you will be required to balance the equation. Does that make sense? So you should be able to write a balanced equation with no problem. Alright, so I'm going to start off the equation with alpha. And let's say you have a parent nucleus of 23892 uranium, and you are converting it into 234 thorium 90 plus 42 helium. So note that the numbers are balanced, and this is your alpha particle. Make sure to balance both your proton number and your nucleon number. So we're going to move on to beta decay. So there are two types. We'll start with the beta minus, which is the more familiar one. Let's say you have carbon 14, okay, and this one converts to nitrogen 714, okay, plus minus 1. And this is your electron or your beta particle, okay. And you have this extra little thing tagging along, okay. I'm going to name them for you. This is your beta minus particle. And this thing, this is what we call an electron anti-neutrino. Nani? How do we know this thing is there? The nuclear number is 0, the proton number is 0. Never mind, other numbers are not 0. We will see later in the second lecture. Okay, so for beta plus decay, you might have Mg, and it becomes sodium. Okay, so you can see the proton number has gone down by 1, so you have to release a beta plus particle. So the beta plus particle is also known as the positron, but I shall put this as the beta positive, okay, because of the positive 1, and then the other one will be beta negative. But normally if you don't mention what beta it is, then it has to be negative lah, guys. Okay, so this would be beta negative particle, and this one is the electron neutrino. Now what I would like you to notice is that these things come in pairs. So for example, the beta negative particle is a legit particle, it's an electron. So the anti-neutrino is an anti-particle. So the pair is come together, one particle, one anti-particle. For example, the positron is an anti-electron or an anti-particle, and the neutrino is a particle. So they come in pairs because there's another number to balance. Again, we'll see it later in the second lecture. Okay, and the final one, you have gamma radiation. I'm just gonna give you an example, because gamma doesn't change the nucleus. It only transitions the nucleus into a lower energy state, releasing some energy. Okay, so this is your gamma photon. Alright, and those are your chemical reactions written down in equation form. You just need to know how to balance them, because sometimes you might release more than one type of particle, or more than one helium, or more than one electron. Okay, that's all. I will see you in the next video for what on earth is a neutrino? Why is a positron? Okay, see you then. Bye bye.